Oh, drat these computers. They're so naughty and so complex. I could pinch them.
What's up, everyone, and welcome. In this episode, we're going to talk about cross-site scripting. Cross-site scripting has been around for over 15 years, but is still used to wreak havoc on web systems worldwide. One of the most famous attacks was back in 2005, Myspace, called Samy. It affected over 1 million people in 20 hours. Other notable cross-site scripting exploits include eBay in 2017, Uber in 2016, and the DuckDuckGo search engine. Cross-site scripting is often said to be the most common vulnerability, and many sites are affected. This includes small local sites as well as giants, including Google. OWASP still lists cross-site scripting among the top 10 most common critical vulnerabilities, even after being around for well over a decade. That's what we want to take a look at today. Before we jump in, let's look at the agenda. We're going to start off with the definition. What is cross-site scripting? In order to build a good defense, we must intimately know our enemy. We're going to then go on to the anatomy of the attack. How does it work? If we know the pieces and how they work, we can evaluate where we are vulnerable. We're going to then go look at some companies that have been attacked. We're going to learn from the fallen. We're going to review some notable companies affected, what their response was, and see if we can determine what their weakness was and evaluate its place within our organization. We're then going to go on to what can I do? We're going to look at steps to improve, including how to implement measures that either fix for good or continuously scan systems to ensure it does not happen again. So what is cross-site scripting? Cross-site scripting attacks are a type of injection in which malicious scripts are injected into otherwise benign and trusted websites. Cross-site scripting attacks occur when an attacker uses a web application to send malicious code, generally in the form of browser-side script, to a different end user. Flaws that allow these attacks to succeed are quite widespread and occur anywhere a web application uses input from a user within the output it generates without validating or encoding it. An attacker can use cross-site scripting to send a malicious script to an unsuspecting user. The end user's browser has no way to know that the script should not be trusted and will execute the script anyway. Because it thinks the script came from a trusted source, the malicious script can access any cookies, session tokens, and other sensitive information retained by the browser and used with that site. So since the script is injected in the web page from that domain, it has access to the cookies and sessions from that domain. These scripts can even rewrite the content of the HTML page. The main purpose of the attack is usually to steal other people's identity, like cookies, session tokens, and other information. As we know, cookies help us log in automatically. Therefore, with stolen cookies, we can log in with other people's identities. This is one of the reasons why this attack is considered as one of the riskiest attacks. It's important to know that there are generally 3 categories that are mentioned or discussed when talking about cross-site scripting. There's what's called a stored cross-site scripting, also known as persistent or type 1. There is the reflected cross-site scripting, also known as non-persistent or type 2. And then there's the subset of the reflected, which is called DOM-based cross-site scripting, also known as type 0. Stored cross-site scripting generally occurs when user input is stored on the target server, such as in a database or a message form or visitor log or comment field, etc. Then a victim is able to retrieve the stored data from the web application without that data being made safe to render in the browser. With the advent of HTML5 and other browser technologies, it could be possible that the attack payload gets permanently stored in the browser, such as HTML5 databases, and then it never gets sent to the server at all. So in stored cross-site scripting, basically the malicious code or the call to the malicious external JavaScript code is stored in the database. When I visit then, or somebody visits, a victim visits the website that shows me that particular comment or product review or whatever I entered in as the malicious attacker, that code or the link to that JavaScript code is also embedded in the HTML and executed as part of the web page itself. The next is reflected. Reflected cross-site scripting occurs when user input is immediately returned by a web application in an error message or search result or any other response that includes some or all of the input provided by the user as part of the request. Without that data being made safe to render in the browser and without permanently storing the user-provided data. In some cases, the user-provided data may never even leave the browser. So, let's say I want to visit a search page for some product I'm interested in, but the link I'm using has malicious code in the query string. It's inside the URL. The infected web page or the vulnerable website takes that entire query string and dumps it back and says, like the product you've been looking for, XYZ, blah, 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 is no longer available. And then it doesn't sanitize or encode what I gave as parameters for my search link. That would mean that if malicious code, or let's say a link to external malicious code, was within that query string, it would take it, inject it into the HTML page response, and show it to me. So the final DOM-based cross-site scripting was defined by Emmett Klein, who actually published the first article about this issue. DOM-based cross-site scripting is a form of cross-site scripting where the entire tainted data flow from the source to the sink, as they say, takes place in the browser. In other words, the source of the data is in the DOM, the sink is also in the DOM, and the data flow never leaves the browser. For example, the source where malicious data is read could be the URL of the page, like document.location.href, or it could be an element of the HTML, and the sink is some sensitive method call that causes the execution of the malicious data, like document.write. Now we know that there are generally three categories that could exist, generally speaking. There are also subcategories, but it's important to know that multiple exploits can simultaneously exist. You could have one from each, one stored with one persistent, that are running in tandem. Additionally, it's important to know that there could be server-side cross-site scripting and client-side cross-site scripting. Server cross-site scripting occurs when untrusted user-supplied data is included in the HTTP response generated by the server. The source of this data could be from the request or from a stored location. As such, you can have both reflected server as well as stored server cross-site scripting. In this case, the entire vulnerability is in the server-side code, and the browser is simply rendering the response and executing any valid script embedded in it. Client-side cross-site scripting occurs when untrusted user-supplied data is used to update the DOM with an unsafe JavaScript call. A JavaScript call is considered unsafe if it can be used to introduce valid JavaScript into the DOM. This source of this data could be from the DOM, or it could be have been sent by the server via an AJAX call or a page load. The ultimate source of the data could have been from a request or from a stored location on the client or server. As such, you can have both reflected client-side server scripting and stored client cross-site scripting. So we just went through a lot of technical jargon. So how does it work? What does it do? We know that cross-site scripting attack means sending and injecting malicious code or script. And this malicious code is usually done in browser languages like JavaScript, HTML, HTML5, VBScript, Flash, etc. Let's walk through three examples, one for each one of the categories we mentioned: stored, or also known as persistent; reflected, also known as non-persistent; and DOM-based. That way we can really visualize in our mind how this works. We know that persistent cross-site scripting gets its name from the fact that malicious code is stored in the legitimate website's internal database. And it's done through comments, blog posts, and events, even tweets. Essentially, any form that accepts user text input is a possible persistent cross-site scripting attack vector. So let's say you have a website, and then I have an attacker or perpetrator. The perpetrator discovers that this website has a vulnerability that enables script injection. For example, a vulnerability that allows HTML tags to be embedded in the site's comment section. What does he do? He infects my website. He injects the website with malicious script that steals each visitor's session cookies. What does he do? He writes a comment. Within the comment is the script source, hacker site, blah, 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 authstealer.js. That's part of his comment. It's stored in the database. An unsuspecting victim or visitor comes to the website, and the malicious script is then activated for that user, stealing that user's session cookies. And bada bing, bada boom, the visitor session cookies is sent to the perpetrator. Next we have the reflected or non-persistent. We know it's also known as non-persistent, and it occurs when a malicious script is reflected off of a web application to the victim's browser, kind of like bounces off. It doesn't stick. The script is activated through a link, which sends a request to a website with a vulnerability that enables the execution of the malicious script. So again, we have our website, we have our perpetrator, we have our victim. The perpetrator this time sends an evil email with a malicious script as a link. So a link to your bank.com, and then there's some kind of evil website with an attack.js. The unsuspecting, unwitting website visitor / victim clicks on the link, sending the request to the vulnerable website, yourbank.com, let's say. Now, the website itself, or the web server, is vulnerable and essentially takes the data from the request and includes it in the valid web page response. Kind of like the search example I mentioned before. I click on a link that's supposed to search for a product that's perfect for me. Within the link, I don't realize that there is some kind of malicious code. The website also is not designed or developed properly to sanitize the query string. Just takes whatever's was in the URL and then slaps it into the legitimate HTML and shows it to me. The victim's browser trusts this attack script is from yourbank.com because it's inside the HTML, right? It's being injected there, and now the attacker has full access to the victim's account because the session cookies, session variables, and cookie information is being sent to the perpetrator. Finally, we look at the DOM-based cross-site scripting. In the example of DOM-based cross-site scripting attacks, there is no malicious script inserted as part of the page. That means the original page, the response page I get, is fine. There's no malicious code in there. The only script that is automatically executed during the page load is a legitimate part of the page, like on-page load, as an example. The problem is that this legitimate script directly makes use of user input in order to add HTML to the page. Because the malicious string is inserted into the page using inner HTML, it is parsed as HTML, causing the malicious script to be executed. Again, we have our website, we've got our perpetrator, and we have our website visitor. And again, I send an evil email with a malicious script as a link. The website visitor clicks on that, sending the request to the vulnerable yourbank.com website. The website still sends back a clean HTML page. It doesn't include the malicious string. Only in my browser, the browser executes the legitimate script inside the response, causing the malicious script to be inserted into the page. So the server knows nothing about this exploit. The server is not essentially, the server itself has no record of this exploit happening. It's all in the browser. The user's browser executes the malicious script inserted into the page by the client side, and bada bing, bada boom, the user's sensitive information is sent to the attacker's server. So we have those three methods, or three ways, three categories of how cross-site scripting can occur. There is stored, that means it's in some kind of form or in some kind of comment or forum post. Then there is reflected, where it is sent as part of the URL and the website unwittingly injects it and allows it to be executed inside the page. So the response from the web server includes this script. And then there's DOM-based, where the web server is not, or web page doesn't have an injected server side. It actually all happens client side. Let's look at some known cases and see what we can learn from them. The first one we're going to look at is the DuckDuckGo search engine. The DOM cross-site scripting vulnerability was on this page 50x.html, and the sink was called the div.innerHTML method, and the source was the search location. The proof of concept URL was this 50x.html, and then inside they put b equals test image source equals error, and then error equals alert document domain. So the code that caused this cross-site scripting was within the library 110.js file. At that time, it was line 26 com6903. And the part of the vulnerable code was this inner HTML loading. And this is the result. The result is that clicking on that URL causes an alert. In this case, it's I mean, it's benign. It really doesn't do anything except to show an annoying alert. But what if this code was extremely malicious, to steal your cookies and send it off to some other domain, or steal your search or any information about your location and send it off somewhere to be stored and track you? So Tweetdeck. So what did they not do? They did not properly sanitize in all instances the variables or the values that they pulled from the query string. Tweetdeck. Twitter had to shut down Tweetdeck in 2014. It's still a long time ago if you think about it, but it's an important flaw, and it's an important case for me to display where some breakages in the links could be that you could check. So the flaw led to the vulnerable versions of TweetDeck. At that time, it was 3.7.1-19002E5. It was running JavaScript code contained in tweets from other sites. So most attacks using the vulnerability, they were just irritations. It was opening up warning dialogues on users' computers. One version, though, created and retweeted itself, and it spread to 38,000 times in 2 minutes. And another changed the font of TweetDeck itself to Comic Sans. So this attack worked for a very simple reason. TweetDeck did not, again, sanitize user input at all under certain circumstances. The attacker didn't discover a clever way to fool the cross-site scripting. TweetDeck had cross-site scripting, but it wasn't being used all the time. He didn't fool it. He found a way to turn it off or to skip it. They found a way, or he found a flaw where it was skipped. The attacker discovered that the Unicode heart, which gets replaced with an image by TweetDeck, somehow prevented or skipped the tweet from being HTML escaped. Now, one potential reason for why, although this is not confirmed, but one potential reason is that the Unicode heart disabled or skipped the HTML sanitizing because they wanted to render it as an image, which, again, the image tag in sanitizing the string would be stripped by the sanitizer. Now, that's just a hypothesis. It would be a bad reason because there are plenty of ways to overcome that, including first sanitizing input and then converting it to an image. But that's how they did it. And the last one I want to talk about today is the Mcdonald's hack. Now, I found this twice under different bug bounty users. One was Amel NSPQR, the other was Thomas Solita. They did report it for the fast food chain through their responsible vulnerable disclosure platform, openbugbounty.org. This cross-site scripting flaw posed a serious potential for danger to the company and users of the affected website. They exploited the search. Within the search, again, it wasn't sanitized properly. So they created a constructor, and the constructor created an alert, and the alert had the content of Open Bug Bounty. And boom, there you see on the McDonald's website from the Open Bug Bounty screenshot that an alert was triggered. Now again, this could be anything malicious. This is a benign test to see if it works. Anything malicious, I could, as an attacker, sending out links to tons of people, get your free McDonald's, blah, 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 click on this link. That link leads to the search, and within the link of the search is that malicious code that could be infecting or stealing cookies or whatever information I have access to from the McDonald's domain. Other notable cases are, of course, the Google WebKit that was had cross-site scripting vulnerability in 2012. It was CVE 2012-4563. Older versions of Apache web server. So the web server itself could have vulnerabilities or had vulnerabilities, and that's older than 2.0.63 and 2.2.10. There are plenty of CVEs about that, different cases. Apache Tomcat, older than 4.1.37. AngularJS framework, Bootstrap, Joomla, WordPress, Drupal, they all had and have, depending on which modules and plugins you're using, cross-site scripting vulnerabilities. So how do you stay safe? OWASP, the organization OWASP has an extensive list of steps to take to ensure known cross-site scripting attacks cannot happen on your systems. However, to summarize all of their lists from the various types of cross-site scripting, I would say that there are three main areas. One is to employ a combination of validating, filtering, encoding, and escaping methods to prevent untrusted user input from executing on the web app. You want to move to frameworks which automatically escape cross-site scripting by design. If you look at recent versions of Ruby on Rails, although I don't use it, but I do use React.js. You want to enforce secure headers, such as well-considered content security policies. Now that is web server hardening, which we will discuss in an upcoming episode. If you want to talk about the specifics, so those are the three main categories or main areas where you can improve. Here are some specific things you can do that all fall within one of those three categories I just mentioned, or three areas. You want to never insert untrusted data except in allowed locations. You want to HTML encode before inserting untrusted data in HTML element content. You want to attribute encode before inserting untrusted data into HTML comment attributes. You want to JavaScript encode before inserting untrusted data into JavaScript data values. CSS encode and strictly validate before inserting untrusted data into HTML style property values. URL encode before inserting untrusted data into HTML URL parameter values. Sanitize HTML markup with a library designed for the job. Avoid JavaScript URLs, prevent DOM-based XSS cross-site scripting, use HTTP-only cookie flags, which is essentially a web server setting, implement content security policy, web server setting, use an auto-escaping template system, and properly use modern JS frameworks. So those are specific steps. And we're going to jump back to general, overarching steps you could take. For those of you who've seen my other episodes, this is going to be very familiar for you. You want to have a plan. Have a plan for your updates, a plan for your maintenance, a plan for your security, a plan of when you're going to review all of those things. Only then can you be prepared in terms of have an understanding of what you're using and what to do and where to look. You want to harden your server to ensure uploading of files is strictly controlled, like JS uploads as an example. You want to scan code, files regularly, looking for known patterns and functions used in these types of attacks. You can also scan your database in terms of looking for this type of content. You want to look at last change dates on files in case the injection is physical, on the, not necessarily a database, but inside any one of your JS files. Or HTML files. You want to make time for regular offline backups. Backup. You want to make backups of your backups. You want to make backups of your backups of your backups. You want to deep freeze a backup of your backup of your backup of your backup. And you want to test to ensure they can be restored from reliably. If you make backups and they're all corrupted, then they don't do you any good. You want to update your systems and third-party libraries or frameworks regularly. This goes into one of the main criteria or main areas that I just mentioned. You want to use modern frameworks, and you want to make sure you're using the most up-to-date and secure version of those. So there you have it. Cross-site scripting in a nutshell explained. I hope you learned something and enjoyed this video. I do appreciate you continuing to join me on this journey, and I look forward to seeing you on the next video. Take care.
Don't forget to ride!